Hello, my name is Dominic Finelli, and this is my presentation for Physics 2211 Lab Number 3, Black Hole. Introduction. The goal of this lab is to find the mass of a black hole using a star's orbit, and then using the mass of the black hole to calculate the initial velocity your ship must need to fly off of a planet and around a black hole without crashing into either. This lab makes use of the momentum principle and Newton's universal law of gravitation. The momentum principle and universal gravitation. These two principles are imperative to this lab, as the momentum principle is used to calculate the velocity and position updates of the spaceship, and the universal gravitation is used to calculate the force of gravity the black hole exerts on the ship. And these two are represented by these formulas: F equals G times M1 times M2 over R2, and F net equals the change in P over the change in T. So firstly, we have to calculate the mass of the black hole. And these are initial conditions. The mass of the star is 2.0 e 30 kilograms. The observation point starts at 0 seconds, and the change in time is 86,400 seconds, which is equal to 1 day. And then, of course, we have the gravitational constant. And this is the code starting from this line, goes down and calculates the mass of the black hole all the way down here at the last line, which is this equation right here, which is then printed. So the results of running my code, the black hole had a mass of 8.08 e to the 33 kilograms, and F net was 8.13 e to the 28 newtons. F net par was 8.38 e to the 27 newtons, and F net perp was 8.12 e to the 28 newtons. And as you can see, this was the end result after running my code. Calculating the initial velocity of the ship. So now that we've calculated the mass of the black hole, we have these initial conditions for the initial velocity of the ship. The black hole mass is 8.08 e to the 33 kilograms. The planet's mass is 9 e to the 28 kilograms. The ship mass is 7 e to the 10 kilograms. The gravitational constant is the same, and delta t is 1. And here are the initial conditions for the planet down here as well, which are already in the code. So to calculate the initial velocity of the ship, we first have to calculate the net force, which is done through all of this code down here. We get down here to the bottom, and the net force on the ship is represented by this equation, which is ultimately what we needed. And then we use Newton's second law for the position and velocity update formulas. So as you can see up here, we have the planet velocity and the planet position, and then the ship velocity and the ship position, which are used to, these formulas are used to update both of those values to actually make the code move. Calculating the initial velocity of the ship, final results. So my results for the initial velocity were negative 5.48 e to the 6 meters per second and 7.22 e to the 6 meters per second. The closest the ship got was to the black hole, which was, the closest the ship got to the black hole was 5.64945 e to the 9 meters, which would probably be around here right at the top. Potential errors. I used the guess and check method for the initial velocity of the spaceship because I was not able to figure out a way to calculate it myself, so that could have led to some discrepancies, and my code could have ran longer for more accurate results. I could have had this run longer so I had a longer view, more accurate view of where the ship and the planet went. What does it mean? How are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? Well, net force is equal to the change in momentum over the change in time, whereas net momentum is just the final momentum minus initial momentum, or mass times velocity. What if? Instead of wanting to take a quick look at the black hole and leave, you want to enter into an orbit around the black hole. What initial velocity would your spaceship need in order to enter some kind of orbit around the black hole? Your spaceship could still not crash into the black hole nor crash into the planet. In order for this to be possible, the spaceship must have a similar initial velocity to the velocity of the planet. So the orbital velocity of the planet is 7.35772 e6 meters per second, and I calculated the ship's initial velocity to be negative 3.2 e to the 6 meters per second in the x direction, and 7.32 e to the 6 meters per second in the y direction in order to enter orbit, as you can see here. I used the guess inject method for this as well, which could lead to some discrepancies, but overall I got a fairly accurate result. That is the end of my presentation. Thank you for your time and goodbye.